So now we're going to talk about the fact that once you have the torques and you can calculate them, and they might be at some angle, once you have those and they're positive and negative, you want to add them up from all the different forces, right? And that'll tell you about the angular acceleration of the object. So the sum of the torques, just like Newton's second law, F equals ma, right? The sum of taus is I times alpha. And then in terms of alpha, like there's a couple different scenarios that I'm just going to go ahead and bring here that we'll see in this class. We've seen these before, like in rotational kinetic energy. But one is this fixed rotation where alpha, it really is just some angular acceleration around the pivot point. But we'll also have cases like rolling without slipping, where there's some alpha, which is caused by a torque that's the same as the acceleration the center of mass gets, divided by the radius of the object that's spinning or rolling. We also have things like rotating pulleys, where alpha is going to be like the acceleration of the rope that's going around the pulley divided by the radius of the pulley, right? And those can be combined with other things moving, like blocks and stuff, like what we did with pulleys before. So I want to just do a quick example where, again, we have to calculate a torque that actually has an angle in it, and then we can find an angular acceleration, right? And so that's the pendulum. So we've done the pendulum before in terms of energy, right? So let's just think about it, though, in terms of torque. So if I have the pendulum, and you can go ahead and say something like it has mass m and a length L, and we'll just treat the weight on the end of the pendulum like it's a point mass, because the length is longer than its radius, much longer than its radius. What would be the angular acceleration of the pendulum if you pulled it up to some angle theta? Okay, so we should have all the pieces for this already. So why don't you first take a minute to think about it, and then we'll bring it back together and make sure we're all getting set up in the same way. No, I is the moment of inertia, right? So we saw this before. So the same thing as like moment of inertia for that we used for rotational kinetic energy or angular momentum. And then alpha is the angular acceleration. Okay, so I hope everyone's at least had a minute to think about how they would want to get started. So I'm going to sort of model the beginning, right? So I just have I'm going to go ahead and draw a picture. It's always nice, right? I have some pendulum. It's out at some angle theta. I'm going to go ahead and call it M and L for the mass and the length, right? And I'm going to need to think about the torques, right? So I have to figure out what the torques are on this mass. So to do that, I do need to think about what the forces are. So it can actually be helpful to draw a diagram with the forces, right? Well, there's some tension along the string that's holding it there. And then there's a force of gravity down. And then when you do these diagrams, like I know when we did the force unit, we always just had a single point that we drew the forces at. But now that we're having to worry about torque, it's actually good to draw a more extended object and actually draw the forces that are acting where they're acting. But it's just that in this case, I'm worried about this mass, and I'm going to just treat it like a single point, so the forces both act at the same place. Okay, so then I need to figure out what the torques are, right? So I have to write down the sum of the torque. So I can think about the forces one by one and figure out what their torques are. So there's T and FG. Well, so I should probably think about what my R vector is, right? So that's going to point from the axis, which is going to be there, because we know it's going to rotate around where the pendulum's attached, right? Because that's where you get the circular path of the rotation around that point. So that's my axis, which means my R vector is going to be down along the string, right? It's basically the length of the string, right? And the magnitude of R is just going to be equal to L. So then if I'm doing the torque, so I can think about the tension, right? So it has both forces actually have the same R vector because they're both the same, acting at the same place, right? But the tension points back along the string, right? So it points exactly in the opposite direction of R, right? And so when you have that case that it's exactly opposite, right? Then you also don't get any torque. And you can think of it a couple ways, right? One way is that it's the sine of the angle between them, which is 180 degrees, which gives 0. Or just the fact that there's no perpendicular component of R. If you follow the tension back, you'd actually cross the axis, right? So if the force points towards or away from the axis, you get 0 torque, right? Or that there's no component of the torque or the tension that's perpendicular to R. Right, so the tension part gets 0 torque. But then there's the part for the weight, right? And so the weight has some different angle with respect to R. And I think actually probably the easiest way to do this is the first way I wrote down, where if you draw FG on here, it's straight down. R is down and to the right. And the angle, just like the physical picture, is theta between them. And so if I make my clockwise be positive, since that's the way it wants to rotate from the force of gravity, right, then the forces here will just be the length times the magnitude of the force of gravity, which is mg, right, times the sine of the angle between them. Right, and then this equals I alpha. And so we're trying to find alpha, and we're just saying we know things like the length and the mass and the angle. And so the last thing is we just need to figure out what I is. Right? And so what's I for a point mass out at some distance? Right? That's just going to be, right, I is ml squared. So I can put all this together, and I can say lmg sine theta is equal to L squared alpha. The m's will cancel. I have to divide by L squared. And so I will get alpha is G divided by L times the sine of the angle. Yep. I can move it a little closer. And it also, hopefully we'll get a better resolution if I back out of the frame for a second and stay still. Right, so this is a relatively simple torque problem with angular acceleration. You just had a couple forces and you had to think about what your R vector was, what angle the forces make with it, what torques do they give you, and then how much angular acceleration do you get out of that. So the question is, since gravity pulls down, would the angle be sine 90 minus theta? So it's not in this case. There are it depends on how you're measuring the angle. So I measured this angle from the vertical here. So theta was the angle up from the vertical. So the easiest way I thought in this case to do this one was to do the case where you move. I draw another picture where I move the force of gravity and the position vector to be starting from the same point, in which case that looks just like the physical picture. And so you can see that that angle's theta. And that's the angle between them. You could also do it based on the perpendicular distance. So the other way to do this is you extrapolate the line that gravity acts along up, and then there's a horizontal distance, r perpendicular, which again is the sine of theta, because that's the side that's opposite the angle. The tension is 0 because the tension points exactly opposite the position vector, right? So because they're exactly opposite, you can think about it. One is the sine of 180 degrees is 0, or that you can think about it that if you drew the line through the tension, it would actually get to the axis, right? And so there our perpendicular is 0 because it gets exactly back to the axis point. So any force that points at the axis or away from the axis, right, will never give you a torque. All right, any more questions on this? Okay, so next, why don't we take a look at a couple of videos? And so I want to say, have you ever thought about why, if you watch like somebody who does like a tightrope walk and they're balancing, right? Why do they like to use these huge poles that bend down like that under their weight to help keep their balance? There's a couple of different ways you can think about this, but one of them is having to do with the torques that it can cause. So this is just a video of this guy who walked across the Grand Canyon a few years ago on a tightrope. So there you go. Another good way that's a little closer to what we can actually do in this class with the problem is to take a look at this toy. So here's our tightrope walker with his weights. And if you pull it down and let it go, it'll just go back and forth. It doesn't want to just fall, right? It wants to keep going. And if there's friction in this, it'll slow down as it goes, right? And eventually it'll right itself and be balanced again. So we can actually figure out why this is happening, why this is a stable setup, by doing a little problem. So here's my simplified model for one of these things. So I have two masses, and I'm just going to put them out at the end of the pole, kind of like that toy had, where there's all the weight was basically at the ends. But I'll just make mine be straight lines that connect back to a single point that forms the axis about which it's going to turn. Okay. And these things aren't, right, they're down. So there's a horizontal line, and then they start off down by theta. Right? And there's two masses, so there's two torques. And the one on the right would want to pull it down on the right side, so that would give you a clockwise torque. The one on the left wants you pull down on the left, so that gives you a counterclockwise torque. Right? If they have the same mass, they have the same distance, right, and they're down at the same angle, then that's balanced. But we want to think about what happens if you unbalance it and then let it go, right? So what if you moved it away from that configuration by an angle phi? So let's say you move the right down and the left up by phi. And for now, we're just going to think about this as a fairly small. So phi is anywhere from a very tiny angle up to like making it horizontal on the left. I think that's the easier way to picture it. And I want you to take a minute and think about this. You know, go with your notes that you should have and draw some pictures. Figure out what the angles are. Figure out what the torques are from each of the masses. And tell me if when you change this angle like that, does the left mass's torque increase or decrease in magnitude? Don't worry about the negatives and positives here. So let's just think about the magnitude, because clearly one of these has to be negative and one has to be positive, because they want to go in different directions. Okay, let's just take a little bit more if you're still thinking, and then we'll talk about it, and then we can think some more maybe. Okay, so let's see. 3, 2, 1. All right, so increase is the more popular answer. It's about 2/3 to 1/3. So why don't we start stepping through this? Make sure you think about this carefully. I'm almost out of paper on this one. Okay. So I'm going to draw two pictures that'll represent two cases. I'm going to exaggerate the angles a little bit compared to what I put on the slide to make it a little easier to see. And I'm just going to draw the left one. So in one case, it's down here with a big angle. Right? And then there's the force of gravity. And the position vector is just the axis to where the mass is. Right? So this is the big angle. Right? And the other one, you have the same length of r, right? But you have a smaller angle, the same magnitude of gravity. Right? And we talked a couple different ways about how you can find, right, the torque from the cross product of these two. Right? And so one way was you had to find the angle between the two vectors. Right? And so one way you could do that is you could redraw it. Right? And there's some angle between them here. And actually, I didn't do a very good job of drawing this one. Let's redo this. Right? So in this case, you have a bigger angle between them. Or the other way to do it, right, is to go back along the line of the gravity and figure out which distance is bigger. Right? So why don't we think about this again? I want to see if everyone's answer stays the same or if you want to change your answer. So remember, the one on the left with the bigger, so that's the angle below the horizontal is bigger is the starting point. This is the after. So before is on the left, after is on the right. Because the angle is getting smaller. The angle to the horizontal gets smaller. All right, why don't we just take another minute and we'll talk about this again. All right, so why don't we bring it back? So I'm a little in. It's a little interesting actually what happened to the responses. That's not quite what I expected. Because the majority was right before, and I don't know if people tried. Some people might have tried to game the system, thinking I was saying, "Oh no, you were wrong," when you weren't. But yeah, so let's talk through this again to make sure, because I just want to make sure everyone's on the same page with this. Right? There's two ways to look at it that I think are both reasonable for this problem. And there's also the third way, which we could do if you want, but it's a little harder to visualize. In one case, you have a bigger angle down from the horizontal. That's the starting case, right, where it's theta. Then since the phi makes the left one go up towards the horizontal, right, this is the after, where the angle is smaller, right? And so there's two things that change. So one is if you take the vectors and you draw them from the same point, the angle in the before case between them is smaller than in the after case, right? Because the gravity's down, and so when the angle for the r vector goes more horizontal, right, the angle between them gets bigger, right? Bigger angles are bigger sines of angles, and so bigger angles are more torque. So you get more torque in the after case, right? So increase was correct. The other way is with the r perpendicular. Since gravity is straight down, you can draw the vertical line, right, through the gravity force, right? And the vertical line gets as close as possible to the axis when it crosses the horizontal line through the axis. That's as close as it can get. And in that case, that distance is r perpendicular. And r perpendicular gets bigger, right, when this gets closer to being horizontal. And actually, a good way to see this, if you just imagined, not that you lifted it up halfway or so, but if you lifted it up all the way so that it was exactly horizontal on the left, right, that would be the most radius you could get, the most r perpendicular you could get, right? And since you're going to be increasing all the way to the max, right, it's not that it's going to decrease and then re-increase again, right? You get an increase all along the way up towards the horizontal, right? So the magnitude of the torque on the left will increase as you go towards the horizontal. Is there any questions about that? Okay, that looks good. So why don't we try thinking about the right mass instead. Does the right mass increase or decrease its torque? No, the torque on the left increased, right? The angle between the torque, between the force and the position increased. The angle got bigger, so the sine of the angle got bigger. The other way to think is the perpendicular distance from the force to the axis got bigger, so that also makes the torque bigger. Right? Because the maximum torque is when one of these masses is horizontal, right? When it's exactly on the dashed line on the left. That's the most torque you could get from one of them, right? Yeah, so why don't we just take a few more seconds. Okay, yeah, 3, 2, 1. Yeah, good. So the majority says decrease, right? Which is the right answer, because it's exactly the opposite situation as the one on the left. You put this in a mirror, right? Just so that they all are on the right instead of on the left. But the real important thing is not, is it on the left side or the right side of the picture? It's what's the angles, right? And for the one on the right, it's the closer to the horizontal is the before, and the farther from the horizontal is the after. So it's the opposite of the left one, right? And the one we said where it's closer to the horizontal has the bigger torque. So when it gets farther away from horizontal, has a smaller torque, right? And the way to get that to the extreme is if you imagine that you rotated it all the way so that the right mass was straight below the axis, right? If it's straight below the axis, it's like the tension in the pendulum problem we did, in that it's pointed directly on a line from the axis to where the mass is, right? And since they're on a line, you get no torque, right? So you go all the way down to 0 if from torque from the right mass if it's exactly below. Yeah. And you could go and actually do this with a bit more math and writing down formulas to get it for other angles. It's a lot harder to visualize it once you go past the left one being horizontal, but you can do the math and you'll find that it will still want to go back the opposite way from the angle you've displaced it, even at bigger displacements, which is what we saw with the toy, right? The toy, like you really pulled it around and it still wants to go back and forth. Okay, so we should cut there. And then there's a few more things I wanted to talk about, which will help lead into next time. Oh, wait, no, sorry. Not another question. Well, actually, is there another question, I guess? And then we'll have a few more things to do before the end of class. Okay, so sounds good. So yeah, why don't we go on? Like I said, you could go and do this and actually figure out like what the difference is with some arbitrary theta and phi, but we're going to skip that. I just want to mention a few more things. We've talked about rotational kinetic energy before, and so just like we had work with force times distance giving you 1/2 mv squared, you also get that torque times angular distance does that and increases the rotational kinetic energy. And in particular, I do want to talk again about rolling. We had this rolling where that v was omega r. Well, this also means that the acceleration is alpha r, right? Because that's just the time derivative of v and omega, and the radius doesn't change, right? And so this means you do need a torque if you're accelerating as you roll. And then that torque comes generally from the friction, right? So you'll have some force pulling you from the center of mass, or maybe it's going down a track, and this is actually the force of gravity, right? And then that gives you a static frictional force, which is what speeds you up angularly. But you should notice that it does not actually remove energy from the system, because that same force, you can think of it as doing both a sort of rotational work, making it speed up how fast it's spinning, while it actually also does a negative work for the translation, because it's in the opposite direction of the translation, and so it actually subtracts from your 1/2 mv squared. And this is why when we did the rolling in conservation of energy, we said the energy was conserved, even though you did need some force to cause a torque, right? It's just changing the energy from 1/2 mv squared into 1/2 I omega squared. Okay. The last thing I want to spend today is a bit highlighting the importance of choosing the axis when you calculate the torque. Okay. So far we did problems where it was more or less obvious, right? They're basically like a pendulum. And so you say there's a fixed axis, it's going to rotate around this. But we'll be doing problems, especially at the rest of, towards the end, Thursday and Friday, where this is not necessarily the case, and you need to think about what axis you want to pick. So I want to show you this video, and we're going to think about what's going to happen. Okay, so we have a spool with a thread wrapped around it. And this is a picture the guy drew on the video of how this is set up. So you're pulling the thread with the tension out from underneath the inner circle. And then there's the outer wheel, which is what's rolling on the floor, right? And this is, he actually put this together with some string and some Lego wheels here. Right, so you see that. I'm going to pause for a second. Okay. So the rope is wrapped around the middle, right? So when you pull on it, it wants to unwind or wind. That's actually the question. But the point is it wants to, when it rolls, it will either wind or unwind the string. So if the string is wrapped around this inner circle and it pulls out the bottom, like in the picture he showed, and then he pulls it horizontal to the table, the question is, which way do you think that the wheel is going to roll? Is it going to roll toward the pull or away from the pull? And the hint I'm going to give you as you think about this for a second is think about the torques maybe instead of the force of the pull. For this one, it's definitely okay, I think, if you just want to give your gut reaction. So let's just take a few more seconds. Okay, so 3, 2, 1. Okay, so the majority think that it will go away from the pull. So let's watch.
String wrapped around it. Pretty simple. You see, when we pull the string, it gets pulled towards the string. Now the interesting thing, and we have the string wrapped around it. Pretty simple. You see, when we pull the string, it gets pulled towards the string.
So it went towards the string, towards into the pull as it went, which is a little unintuitive, which we could see from the poll, right? This is totally what I expected people to think, because you think about this and you say, oh, I'm going to pull and the string is going to torque it, right, around so that the pull, and it's going to make it want to rotate, in this case, from the perspective we have, clockwise, right, which would make it want to roll away, right? But isn't there another force that could be exerting a torque? Right? There could be friction with the ground. We know with wheels you can have static friction and give you traction. It can make your car go. It can make you brake. It can do all those things. And so it can be complicated to figure out, just sitting down and thinking in your head, what the friction is going to do. And that's exactly what you just saw, is that it did not give you the intuitive thing you think will come from just the string. But there is actually a way to think about this problem that's a little different, which we'll get to in a second. But first, let's look at the rest of this. What happens if you change the angle you pull? So he pulled close to horizontal. What happens if you change it?
The interesting thing is, if you make the angle higher, you can eventually make it stop rolling, and eventually roll back the other way. Yeah?
So if you pull sort of close to up, but still to the left, then it's going to roll away from you. And you kind of have to follow it to make sure you keep the same angle, right? So if you low, it goes towards you. High, it goes away from you. And actually in between, I don't know if he does it here. I don't think so. If you get it just right, it's probably hard with that string, his string, which has a lot of bends in it. If you get it just right, you can actually drag the thing without it rolling at all. And so this really is our first look at why it matters where you pick your axis from. We mentioned this also for angular momentum, right? You have a choice. Where is your axis? This is just like coordinate systems, right? Because our axis, I can specify, that's just telling me where do I draw my R vector from. It's my choice. It can't change physically what's going to happen, but it can make things easier, right? So one way you can do this with wheels is you can actually think about the whole wheel rotates not around the middle, which is sort of the natural thing you would think, but around the point it touches the ground. And the reason you want to think about it this way is because now the friction is acting at the axis, which means the friction does not cause any torque. And that means we don't have to think about it so much if we want to think about which way the thing is going to rotate. Now we just have to think, what direction of torque does the pulling force cause? And in this picture, even though, right, the force, if you were going around the center of the spool, the force would make you want to, looks like it makes you want to rotate counterclockwise. If you go around the bottom, you can see that it actually wants to rotate clockwise, right? Which means it wants to roll it over to the next point that's in the direction of the pull, which is why it goes towards the pull, right? And this isn't a point that'll come back on Thursday. You'll talk about it some more, I think. If you were forced to be around some hinge or other fixed point, like meaning fixed, like it doesn't move at all, like literally it's pinned there, that's probably what you're going to want to use as your axis. And the reason is actually the same. You don't want to think about the forces exerted by the thing pinning it down, right? But if there's some unknown force acting in the object, it actually helps to set the axis where that acts. So it causes no torque. And that's what happened actually is the friction of this rolling object. Otherwise, the center of mass may be a good choice. Okay. Because actually we can see more in this picture from the other scenarios, right? He didn't show this one, but the left one, if you do line the force up with the axis, you get no torque. And in that case, actually, if you pull at that angle, you can just drag the thing because you still get a force to the right from the pull, and then there'll be some kinetic friction to the left slowing it down, but you can just drag it because there's nothing in that picture causes any torque at all. The friction, if you did try to analyze it around the center, what you find is the torques cancel between the one caused by the friction and the one caused by the pulling force. Because the physics can't actually change, just the numbers. But if you go to the higher angle, and I've drawn it pretty much vertical here, but that works, or it works to be anywhere in between the picture on the left and vertical. There, it will rotate to the left, right? Because now you see that the sense of F with respect to the R vector has changed. And so you get torque in the opposite direction. And that's when it starts to roll away. Right? And so that's conjugated. And actually what happens that means is since the pull is still to the right or up, the static friction actually has to switch and actually goes the other way. And it makes it, gives you the sort of traction force like in a car, right? And so that's why it means it's hard to tell exactly what that friction is going to do just from sitting down and thinking about it. And so it actually makes sense to try to eliminate the friction and then think about the torque by moving the axis to where the friction acts. Okay, so again, you'll think more about the axis, I think, on Thursday. And Friday at recitation, you'll be doing a problem like that where you could think about it at different points if you felt like it. But are there any questions about the stuff for today? Otherwise, I'll wrap up there. Okay, looks like not. So yeah, have a nice day, everybody, and we'll see you later.